Now continuing with the alkali metals only, we have got the next part, that is with the exception of lithium fluoride, that is we have just seen it, that reactivity of the alkali metals towards a particular halogen increases in the order. If lithium is greater than sodium, lithium is less than sodium, is greater than less than potassium, is less than rubidium, is less than cesium, while that of halogens towards a particular alkali metal decreases in the order. Fluorine is greater than chlorine, is greater than bromine, is greater than iodine. Means lithium is less reactive, cesium is the most reactive in case of alkali metals, and in case of halogens, fluorine is the most reactive and iodine is the least reactive in nature. So with continuing with that only, we have got, with the exception of lithium fluoride, all other lithium halides are covalent. Alright, with the exception of lithium fluoride, all other lithium halides are lithium halides. Got it? That is lithium chloride, bromide, iodide, all are covalent. Being covalent, LiCl, LiBr and LiR are insoluble in water, but they are soluble in organic solvents like pyridine, benzene, alcohol, ether, etc. Alright. For the same alkali metals, the melting point decrease in the order. Fluorides is greater than chlorides, is greater than bromides, is greater than iodides due to corresponding decrease in their lattice enthalpies. Alright, that is the melting points of sodium halides decrease in the order NaF, which is around 1200 Kelvin, so to say. Then it is greater than NaCl, which is around 1000 Kelvin, in this way. So you find that sodium fluoride is having the highest melting point, we can say that. For the same halide ion, lithium halides being covalent having lower melting point than their corresponding sodium halides. That is they have lower melting point than their corresponding, what you can say, sodium halide, so to say. Thereafter, the melting point decrease due to the corresponding decrease in the lattice enthalpies as the size of the metal increases. Thus, the melting points of alkali metal chlorides decrease in the order NaCl, which is greater than KCl, which is greater than RbCl, is greater than CSL, greater than LiCl. We can say that. Got it? For the same, that is, we can say halide ion, lithium halides being covalent, that is having lower melting point, all the alkali metal dissolve in liquid ammonia, that is to give blue solutions due to the presence of ammoniated solvent electrons in the solutions, we can say that. Due to the ammoniated solvent electron, that is metals dissolves with ammonia. Any metal that dissolve, any metal means I am talking about the alkali metals only, that is in liquid ammonia, are widely used as reducing agent in organic chemistry under the name that is known as Birch reduction, we can say that. Under the name of Birch reduction, it is being widely used, we can say, widely it is used. Alright, under the name of Birch reduction, that is when metals dissolve in ammonia, any alkali metals, that is. So next one, the stability of the carbonates towards heat increase down the group as the basic character of the alkali metal hydroxides increases down the group. That is, Li2CO3 is however less stable and decomposes on heating. Li2CO3 on heating gives you Li2O plus CO2. Alright, stability of the carbonate towards heat increases down the group. Alright, it increases down the group as the basic character of the alkali metal hydroxides increases. Alright, so it is becoming more and more stable, we can say that. So Li2CO3 is least stable, otherwise Na2CO3, K2CO3, they do not decompose on heating, they do not decompose, that will not give you Na2O plus CO2, understood? So lithium forms bicarbonates in solution while all other alkali metals form solid bicarbonates. All other alkali metals, they form solid bicarbonates. All the bicarbonates on gentle heating undergo decomposition to form carbonates with evolution of carbon dioxide. Alright, all the carbonates and bicarbonates are soluble in water and their solubility increases down the group. Alright, all carbonates and bicarbonates are soluble in water and their solubility increases down the group. Lithium differs from other alkali metals. I have said you already that lithium has got an anomalous behavior. It will differ from other alkali metals because of its small size. I have discussed with you, high polarizing power, high ionization enthalpy and absence of d orbitals. Due to this reason, they differ from this group. Lithium shows diagonal relations with magnesium. I have discussed with you due to the similarity in size of their atoms and ions, so to say. Lithium. Now, if you see the extraction of sodium, if you see the extraction of sodium, that is we extract that is sodium by this particular process, we can see that is sodium is extracted. So in this way, sodium we are extracting it very clearly. You can see the diagram there, that is we are using fused NaCl, KCl, KF, or NaCl and CaCl2 are using it as an electrolyte, and the iron pipe is used, we can say that. Wire gauze sodium, we can see that graphite is being used in this way. So that is we are using this down cell for the extraction of sodium, we can say that the down cell, this is known as down cell, which is used for the extraction of sodium. So sodium extracted by the fused sodium chloride by the process called the Downs process. Now the difficulties which is encountered in this particular process, that's although sodium chloride is very cheap and is abundantly available, yet the development of Downs process for the extraction of sodium from fused sodium chloride was delayed because of the following reasons. Alright, it was delayed for the following reason. Sodium chloride melts at 1084 Kelvin and it is difficult to attain and maintain this high temperature. It's very important. Sodium chloride melts at 1084 Kelvin and it is difficult to attain and maintain this high temperature. Sodium boils at about 1156 Kelvin. The next difficulty is that sodium boils at about 1156 Kelvin, and hence at that temperature of electrolysis, the metal liberated will vaporize. Definitely, at such a high temperature, how it will, the metal will remain in the metal state, it is going to vaporize. So the molten sodium forms a metallic fog for that reason and fused with fused sodium chloride, the molten sodium. The products of electrolysis, sodium and chlorine, corrode the material of the cell at this high temperature. Got it? Now, J.C. Down, that is a scientist, he created this cell to overcome all these difficulties which which I just said you, that sodium chloride melts at a very high temperature, difficult to maintain this high temperature. Sodium boils at a high temperature and it vaporizes, rather, we can say that. So it forms a fog with the sodium chloride, sodium metal, it forms a fog, it forms a colloidal solution, we can say that. The products of electrolysis, sodium chlorine, corrode the material of the cell. So to overcome these particular difficulties, he made a cell which you can see it on the screen. The cell, we can say that the down cell, we can say that this is known as down cell. He observed that the addition of calcium chloride and potassium chloride lowers the melting point of sodium chloride. Alright, for that reason, you've used the calcium chloride and potassium fluoride, we can say that. NaCl plus CaCl2 we can use, or we can use NaCl plus KCl plus Kf. Just now I said you. Now, sodium is now obtained by electrolysis of fused eutectic mixture. It is known as eutectic mixture of sodium chloride 40% and calcium chloride 60%. We can say that. So, using graphite anode and iron as cathode. You can see everything is there in the figure. If you see the figure properly, you can see that graphite is used as an anode and iron is used as a cathode, the iron pipe, we can say that. So, where sodium chloride undergoes dissociation and sodium is collected at the cathode, and at the anode chlorine gas is being liberated. Alright, liberated it is. Potassium metal being more soluble in KCl, then sodium metal is soluble in NaCl. Potassium cannot be obtained by the electrolysis of fused solution of KCl, we can say that. It can, however, be obtained by the following two methods only, that is by electrolysis of fused KOH or by the reduction of KCl with sodium. Alright, potassium can be obtained by two methods, following two methods. What are those? By electrolysis of fused KOH, where potassium is obtained at the cathode, or by the reduction of KCl with sodium. KCl plus Na will give you NaCl plus K. Potassium thus obtained is about 99.5% pure. So this is your down cell, where chlorine, you can see from the top, is being evolved, which acts as the anode, and potassium is being collected below, we can say that. That is not below, at the side you can see the recovery for the sodium. So potassium, I'm saying, sorry, sodium is recovered from the side, you can say. So this is your down cell, which in the figure. Alkali metals cannot be extracted by reduction of their chlorides, oxides or chlorides. It cannot be extracted by displacement from aqueous solution of the salts by other metals, or by electrolysis of its aqueous solution of the salts. They are actually prepared by electrolysis of the fused salts, which I just now said you in the Downs process. Alright, for this reason, alkali metals are extracted by the electrolysis process, because they cannot be reduced by the oxides or chlorides. They cannot be displaced by the aqueous solution of the salts, we can say that. alkali metals. So hence they are prepared only by the process of electrolysis of their fused salts only. Got it? Of the chlorides, especially chlorides. So next is this particular method which you can see. It is a Solvay's process. It is a Solvay's process. I am showing you the Solvay's process for the manufacture of sodium hydroxide. That is sodium carbonate and sodium hydroxide. It is a manufacture. The Solvay's process basically there is sodium carbonate, that is washing soda, Na2CO3. It's being prepared by the Solvay's process. So you can see the figure of the Solvay's process. I have shown you there. We are having the ammoniation tower. The first one is the ammonia absorber, that is ammoniation tower. Then we have got ammoniated brine. Then we have got the carbonation tower, you can see after that. And finally we have got the ammonia recovery tower. We are having it. Clear? And at the bottom you can see, that is we are getting the sodium bicarbonate, NH4Cl, and little of ammonium bicarbonate along with it also we are getting it. So mainly in the Solvay's process, what is the principle involved? The principle is based upon, the process is based upon the principle that when carbon dioxide is passed through brine, that is sodium chloride solution, saturated with ammonia, the ions like sodium ions, ammonia ions, ammonium ions, chloride ions, and bicarbonate ions, we get it. Got it? They are being present in the solution, we get it. Out of the various compounds possible, sodium bicarbonate being sparingly soluble crystallizes out. Very important here. Out of the various compounds possible, sodium bicarbonate being sparingly soluble, it crystallizes out. This is finally calcined to form sodium carbonate. We can say that. So if we go to the theory, now this you can see the diagram. I hope you understood this particular diagram. Now if you go to the theory, you can see that here this is the flow sheet diagram I have shown you here, this particular one. That is we are having the OH minus ion, the carbonate ion, sodium ions, ammonium ions, so many ions we are having it. Out of that we are getting only sodium carbonate, we can say that. Finally at the bottom you can see Na2CO3 is being used, we can say we are getting it. Used, I am saying it is being we are getting it. So what happens is that when ammonia and water we are passing it, it forms ammonium hydroxide, NH4 plus and OH minus. So when carbon dioxide is passed through the brine solution, you can see sodium chloride at the top. So sodium chloride at the top when carbon dioxide is passed through it. Got it? So here that is a brine solution, ammonia absorber, you can see that. Ammonia little carbon dioxide, you can see at the top it is written in pink. So what we are getting it? So sodium bicarbonate is obtained, is being formed. Because of the common ion effect due to the presence of Na plus ions of sodium chloride, sodium bicarbonate precipitates out. It is filtered and then ignited to get sodium carbonate. We can say that. So sodium carbonate is obtained above is contaminated with ammonium salts. Sodium carbonate we are getting with ammonium salt, the sodium carbonate. Got it? Because as you can see it here it is sodium carbonate with sodium bicarbonate, ammonium chloride with ammonium carbonate, we are getting it. Okay. So the sodium bicarbonate thus formed is filtered and heated to give pure sodium carbonate. Recrystallization from water produces washing soda, Na2CO3.NH2O. So what is the function of ammonia then? Carbon dioxide is only slightly soluble in water. As a result, the concentration of carbonic acid which is very low. Hence, further, since carbonic acid is a very weak acid, the concentration of bicarbonate in the reaction mixture is extremely low. To shift the equilibrium in the forward direction, it's very important. To shift the equilibrium in the forward direction, a base such as ammonia is used, which combines with H plus ions to form ammonium ions. NH3 plus H plus gives NH4 plus. Thus, the function of ammonia is to produce a sufficient amount of bicarbonate ion, which enables sparingly soluble sodium bicarbonate to precipitate out of the reaction mixture. We can say that. So we have got here ammoniation tower. Let me come to the tower. The ammoniation tower or ammonia absorber. Saturated solution of brine 30% is introduced in the top of the iron tower, while gaseous ammonia form from ammonia recovery tower is passed from below. We can say that. You can see it. Everything is there in the figure. If you look at the figure and listen to me, you will understand it. As a result of this counter current process, brine gets saturated with ammonia, while calcium and magnesium present as impurities in commercial sodium chloride gets precipitated as their corresponding insoluble carbonates. Now in the carbonation tower, it is made up of iron and is fitted with a number of perforated horizontal partitions. You can see that. Got it? The clear ammoniated brine solution is made to trickle down from the top of the tower, while carbon dioxide from lime kiln is introduced from the bottom at a pressure of, you can see carbon dioxide is introduced at a pressure of 1 to 2 atm. Carbon dioxide rises through the small holes and reacts with ammoniated brine to form sodium bicarbonate. The solution then finally is being filtration is being done. The solution flowing out of the carbonation tower contains tiny crystals of sodium bicarbonate. These are filtered by using by passing through vacuum, what you can say, filters. You can see clear, it is being filtered. You can see the filter is being there. There is a black color, you can see, box type, you can see. So the sodium bicarbonate obtained above is heated strongly or calcined in a kiln when sodium carbonate is obtained, which I have said you already. Alright, so the raw materials which is used in the Solvay's process is the Solvay ammonia process. It is quite economical, and the raw materials used except NaCl's and calcium carbonate, all other raw materials used are not consumed in the process. Alright, all of the raw materials which is used is not consumed in the process, because in the ammonia recovery tower, you can see the next tower is ammonia recovery tower. The filtrate from the carbonation tower contains ammonium chloride and a little of ammonium bicarbonate. It is you can see at the bottom it is written ammonium chloride and little of ammonium bicarbonate. So at the bottom you can see it is made to flow down the ammonia recovery tower, while a current of steam is made to go up. Milk of lime is introduced at a point little above the middle of the tower. Ammonia bicarbonate is decomposed by steam and ammonium chloride by milk of lime as follows. Alright. So in this way, that is, potassium carbonate cannot be prepared by Solvay's process. It's very simple, because potassium carbonate cannot be prepared by the Solvay ammonia process. This is reason that unlike sodium bicarbonate, which is sparingly soluble in water, potassium bicarbonate is fairly soluble in water. Thus, when carbon dioxide is passed through ammoniated brine, sodium bicarbonate gets precipitated, while potassium bicarbonate does not get precipitated when carbon dioxide is passed through an ammoniated solution of potassium chloride. Hence, potassium bicarbonate cannot be prepared by the Solvay ammonia process. We can say that. So, now that is sodium carbonate. I have discussed with you all these things cannot be prepared by this process. There is all this, what you can say is that sodium, there is Solvay's process, all the entire process I have discussed with you. Got it? So you can see the reaction NaCl plus water plus CO2 plus ammonia gives NaHCO3 plus NH4Cl, which is sodium bicarbonate is insoluble, but in case of potassium bicarbonate it is soluble. Okay, so hence potassium carbonate cannot be prepared by this method. It does not separate out, we can say that. Pure sodium chloride is not hygroscopic. However, sodium chloride gets wet in rainy season due to the presence of impurities. We can say that. Due to the presence of impurities, it gets wet in rainy season. Impurities are what? Magnesium chloride, calcium chloride, MgSO4 and calcium sulfate, all of which are hygroscopic. Due to this reason, it is what you can say, pure sodium chloride gets wet. Table salt becomes wet. Otherwise, pure sodium chloride is not hygroscopic. Sodium hydroxide is prepared commercially by electrolysis of an aqueous solution of sodium chloride using mercury cathode and graphite anode in a Kastner-Kellner cell. So this is your what you can say, the Kastner-Kellner cell. We can say that this particular one is your Kastner-Kellner cell. In this particular Kastner-Kellner cell, we prepare, that is your sodium hydroxide. So in a Kastner-Kellner cell, we are having, or mercury cathode cell also, we can say that. You can see it consists of a large iron tank divided into 3 compartments by slate partitions. You can see that black one is a slate partitions which do not touch the bottom of the tank. Yes, you can see it is not touching the bottom of the tank. They are suspended in mercury placed on the base of the tank. As I am saying, you go on looking at the diagram, you will understand it. They are suspended in mercury placed on the base of the tank. The anodes are made of stout graphite rods. We can say that anodes are graphite rods, and cathodes are made of iron rods. We can say that. The mercury serves as intermediate electrode as a cathode in the outer compartment and as anode in the central compartment by induction. We can say that. The brine solution is taken in the side compartments. You can see the brine solution in the side compartments is there. in the two sides. In the middle we are having dilute NaOH, and is taken in the central compartment. On passing electricity, the electrolysis takes place in the outer and the central compartment. That is, NaCl gives Na plus plus Cl minus, and water gives H plus plus OH minus. At anode, chlorine is being collected, and at cathode we are getting sodium amalgam. We can say that we are getting sodium amalgam. In the central compartment, sodium hydroxide, being a strong electrolyte, undergoes complete dissociation, while water, being a weak electrolyte, ionizes only slightly. Got it? So in this way, what we find is that sodium amalgam reacts with OH minus ion, which we are getting it from the central compartment, to form sodium hydroxide. So when the concentration of sodium hydroxide solution increases to about 20%, it is withdrawn, evaporated, fused, and finally cast into sticks. We can say that it is being finally cast into sticks, we can say. So this is your Kastner-Kellner cell for the preparation of sodium hydroxide, so to say. So now next is baking soda. NaHCO3 is obtained by saturating a solution of sodium carbonate and carbon dioxide, when sodium bicarbonate, being less soluble, separates out. Baking powder is different. It's a mixture of sodium bicarbonate 30%, starch 40%, calcium dihydrogen phosphate 10%, sodium aluminium phosphate sulfate we are having. Whereas starch is used as a filler, slows down the reaction. Got it? So that carbon dioxide is given off more slowly, we can say that. Now if you come to the biological importance, what we studied just now, sodium ions are primarily found outside the cells in blood plasma and other interstitial fluids, while potassium ions are present inside the cells. Sodium ions help in the transmission of nerve signals, in regulating the flow of water across cell membrane, and in transport of sugar and amino acids into the cells. Potassium ions, which are more abundant within the cell's fluids, activate many enzymes which are responsible for oxidation of glucose to produce ATP. We can say that this is the use of the sodium and the potassium ions in what you studied in this particular chapter, because these are the most important ions, we can say that. Thank you.